So they tell me the probability that somebody actually has the flu is 0.04. So what's probably somebody who does not have the flu? 0.96. And they have 25 people call. So what is this better known as in this kind of problem? Either you have the flu or you don't. So how many possible cases are there? 2, which is where the term binomial comes from. Binomial, 2 possible outcomes. You can word something so that everything has 2 outcomes. So rolling a die, does that have only 2 outcomes? Well, if you say, I want a 5. So 5 or not 5. There, 2 outcomes. I love it. And some of you guys feel like, well, that's cheating. No, it isn't. If you're looking for 5s, there's a probability of getting a 5, and then there's a probability of not getting a 5. Okay. So then you could put it in terms of a binomial probability. 2 possible outcomes. So what symbol would I put here for that probability? What are the parts of a problem? N is the total number as always. There's 2 other letters here for binomial probability related to the 2 possible outcomes. P and Q. X will be the number of successes. P and Q are probability of success. And that's probably a failure. So if you can identify that it's a binomial situation, meaning there are 2 possible outcomes. And remember, even if you roll a die, it could be 2 outcomes. If you're looking for 5s, then a failure would be not a 5. So there's 2 outcomes. That's a binomial situation. Now, this problem says what's probably that at least, this will be P, this will be Q. What's probably that at least 4, right? At least 4 actually have the flu. Now what really sucks about that is to do it though directly, the way it's worded, you'd have to do the probability of 4 plus the probability of 5 plus the probability of 5 all the way up to 25 in this case, right? You guys see that? There's a much quicker way to do this. Because what's the least number of people that could have the flu?
4.
No. In general,
0.
Out of 25 people, you can have anywhere from 0 up to 25, right? Is that cool? So their question is the probability, these probabilities, they want this one. That's the question right there. Is that cool? 4 or more, right? At least 4. Well, what's the opposite of that?
0.
There. I like this a lot better. How many times do I have to use the formula 1, 2, 3, 4 versus, oh shit. It's the same idea as 1 minus none is the probability of at least 1. It's the same idea. So 1 minus 0 and 1 is the probability of at least 2. 1 minus 0, 1, and 2 is the probability of at least 3. Whatever is left out, the rest of it is 1 minus that. So when I add up all these probabilities, what would I get? 1. Their question is, what is the probability of all these? Well, isn't it 1 minus the probability of these? Of course it is, because they add up to be 1. Don't let it be more than that. People make so much out of this, like, oh, this is impossible, I don't understand this shit. They add up to 1. So, of course, 1 minus 1 chunk is the other chunk. That's all it is. And why would I rather do this chunk? Because it's only got 4 calculations versus, holy shit, right? You can see that. And the 1 minus none is especially beautiful. If they said probably at least 1, I'd only have to do 1 calculation and then take it, subtract it from 1. That would be amazing. Okay, this sort of sucks, but this definitely sucks. Right? So you have to do 1 minus the probability of 0, or 1, or 2, or 3. That's what's left out. So let me see, how do you do the probability of 0? Let's just focus on that for a second. What would the probability of 0 be, and what would the probability of 1 be? because then you can do 2 and 3. How do I do the probability of none? How does this binomial thing work? Who remembers? How many people do you have total? 25. And how many of them do you want to choose to do something in this case? None. Yeah. Now, we need to be past this point. So this question, I've interpreted the question and came up with a better way to solve the damn thing. That's awesome. That's always a part of mathematics. Always. All right, you asked this, but it's easier to do this, and then I can get your answer easy. That's beautiful. That's an awesome. That's one piece of math, is to try to come up with the answer the best way you can, the easiest way you can. So you could, all day long, you could do the probability of 4, the probability of 5, all the way up to the probability of 25 and add them all together if you really felt like it. Feel free. But don't complain to me that my test is too long, because it was your choice to make it that long. Does that make sense? I love it. So many guys are like, don't do that to me, Jeff. No, I'm teaching you so you can figure out the quicker way to do something. So probability 0 would be 25 people choose none. So then how many successes do you want? Just said it. None. And how many failures do you want? 25, because that's how many people there are. If there are no successes, in this case, again, to remind you, success doesn't have to be something good. In this case, the success is having the flu. So success is just what they're looking for. It doesn't have to be something to celebrate, right? Yeah, we got the flu, way to go. Okay, maybe. You guys so much. So that means 20. What would the probability of 1 be? 25 choose 1. So how many successes do you want now? 1. And how many failures? 24. It's crazy. So then what would 2 look like? I think you could figure that out. What would 3 look like? I think you could figure that out. If you add those probabilities, you'll get this. What's the question want? This. So you do 1 minus what you just got. Okay. So let's see. Can you guys do this first one for me on your calculator? Figure out what that is. Yes. No. Didn't bring them. You should come, you can get one, rent one, you can check one out from the library. I'll bring them with me on like days I have worksheets or tests. Yeah. Yeah?
I got 0.36, 0.3604.
3604? Alright. And then this one. You guys try to do this one if you have a calculator. If you don't try to do it in your head, man. That would hurt. Say, sorry, 3754. And then, and again, the probability of 2, the probability of 3. Because again, the question they ask would take a lot of computations. If you wanted to do the probability of 4 and the probability of 5 and the probability of 6 and add them all up, that would work. All day long it would work. Does everybody get that? So you could certainly do that. If you just put a 4 in, if you just figure out the probability of 4 and stop, that's not what it's asking. That would be if the question said, what's the probability that exactly 4 of them have the flu? This is the probability at least 4 of them. There's more than one way to do that. You could do 4 or 5, or you have to add them all up. I'm suggesting to figure out the opposite and then subtract it from 1, because that's how opposite probabilities relate to each other. One is 1 minus the other. So let's see, let's try out a smaller problem. And we'll do it all the way out, because I know that some of you guys are like, why didn't you do it all the way? Because this is your work. Let me do an example like this, but I will do all the way out. So let's say the probability somebody has size 15 shoes is 0.07. Why not? Anybody have size 15 shoes? Okay. Didn't know if anybody's tall enough for that kind of action. No. So, and the probability somebody does not have size 15 shoes would then do what? 0.93. Good. I love it. You're all like, is that a trick question? No, it's just a basic question. And if I ask you, we select 11. No, it's not. Let's not make it 11, Jeff. Let's make it something more manageable. Let's say we select 5 people. Find the probability at least 2. Yeah, sure. At least 2 have size 15 shoes. This is basically the same problem as the flu one. Do you guys see? The flu one just had 25 instead of 5. I just want to make it a little more manageable so we can actually see all the numbers. So what would you have to calculate to do this directly? And first off, tell me this. What's N? 5. That's the total number of people we're looking at. What's P? 0.07. Because we're looking for people that have size 15 shoes. What's Q? That's crazy. P plus Q always has to be 1 because together they're everything, right? And then what is, X is going to be a range of things. X is going to be, in this case, X is 2, 3, 4, 5. Do you guys see that? Because how can you be at least 2 of them? 2 of them, 3 of them, 4 of them, 5 of them. I like it. I like it. Okay? So let me do this. Let me do this problem a little bit differently. I want you guys to really see everything here. So there's every possible outcome here. Let's figure out what all the probabilities are. Just because this is a very manageable problem. There's only 5 probabilities I have to do. All right. So let's do this. People from this first row, you guys, can you figure out the probability of 0 for me? Just if a couple of you do it, that'd be awesome. The rest of you can just stare at me menacingly as you are. So here, probability of 0, figure out what that is. This row here, I'll look at you guys. You guys do the probability of 1. I like it. Do the probability of 1. You guys do the probability of 2. Everybody with me? You guys do the probability of 3. I don't know why I did that, but oh well. You guys do the probability of 4. And you guys do the probability of 5. I wish I could take credit for thinking that far ahead to make it work, but I can't. I didn't do that. It just was lucky. Hopefully. If you're not sure what I told you to do, just do something. Figure out one of these probabilities. So you know these. You should be able to set up the formula to figure this out. Ooh, I like it. No, just mine. That's all right. Just hang out. All right, let me see. My first row over there. So everybody got the probability of 0. 6957? Okay, cool. I got a couple of agreements. What about probably 1?
2618.
Anybody else do it? You're.
I don't know if that's right.
Does it sound right? Anybody else do that? Nobody else did it. I love you guys. That's just why she's in the front. Okay. So point 2.
2618.
2618. Okay. What about you guys? This is probably a 2. Anybody did it? I love calling out an entire row of people. Nobody did that? All right. So let's do 2 together. And everybody just stare at that row. How would I do the probability of 2? Yeah, 5 people.
5 C2.
Choose 2 of them to have size 15 shoes. Yeah, 0.07 squared. I want 2 successes, so therefore I want 3 failures. I like it. Alright, somebody able to do that? You remember where this choose is? You do 5, math, probability. Yeah, there are. Number 3, I think, is NCR, right? And then you put in the 2. So 5, choose 2 times, and just keep going. Yeah. 0.0394, I like it. And this one should be 6957. Should it?
Yeah.
Yeah, okay. Okay. Now 3, who had to do 3? 0, 1, 2, 3. 002, I like 0.00, and it'll actually be 30. Damn, because it was 297, so then it's got to go up to 30. 4, did you guess?
0.000011.
0, 0, 0, 1, 1, right?
Yeah.
Okay. So almost basically for any human, that's 0. And then 5, you guys, it went crazy.
0.16807.
But it's times 10 to the negative 6, so you have 5 zeros. So basically this one, if I go to 4 places, that's basically 0. All right. Let me stop here for a second. I'll get ready in the back. All these could shift up, that'd be awesome. All right. Now, didn't we do each one of these probabilities individually? We did not make them up so that they added to be 1. But what do you get when you add all these up? It's going to be at least close to 1 because we had to round a few places. But if you actually do it, it should come out. Does it come out to exactly 1? That'd be kind of neat. 5, 9. Yeah, it does. Cool. Or close to it. Everybody still with me? You guys still with me? So we just use the formula 5 times. This is why you don't want to do this other problem, the 25 people. You don't want to do that this way. My God. In fact, I've done more work than I had to for this problem. I want you to realize that. I did that on purpose. So the question is, at least 2 have size 15. So to do that directly, I would add these together. So if I add these together, I get let's see if I can do it. 0.0425, it looks like. Right, adding these together, 0.0425. And if I do 1 minus these, I'm going to get the same answer I just did. Of course I will, because all of these add to 1, so 1 minus this has to be the stuff I left out. Or, 1 minus this has to be that. So when I have this long-ass list, and they want probably greater than 3 do something, Well, hell yeah, I'm going to do 1 minus the opposite, because then I got a lot less computations to do. Please do that. Maybe. It's that same idea that keeps coming back up. If the opposite probability is easier to calculate, yes, I will do that. And then do 1 minus to get the actual question. I like it. Okay. So this part is a part I would not do on that flu problem. I would do 0, 1, 2, 3, and then do 1 minus that, because that would be what these would all add up to be. I don't have to do all of these then. I just have to get the part that that question leaves out. So this would be a 4% chance that at least 2 people of a size 15 shoot. Okay, I like it. So can you imagine if I had selected 85 people, and I want the probability that at least 2 have size 15? How long would this list be? Holy shit! But I could do these. It won't be these same numbers because now n is 85. But I can calculate these 2. 1 minus that will be all the rest, because all together they make 1. Don't let that mathematical fact trip you up. Let me show it to you a little bit different way, and then we'll move on. So already got what they want from this? More than you ever wanted? So that one problem with the flu, probably 0 plus probably 1 plus probably 2 plus probably 3 plus the probably of 25, that has to equal what? 1. So they wanted to know, what was it, at least 4, right? They want this, they want that answer. That's the answer they want. And there's a lot of computations to do there. So wouldn't I just rather do 1 minus this is not equal to their question? That's it. That's all. They all add to 1. So if I do 1 minus 1 chunk, it will leave the other chunk. So when the opposite probability has less work to do, yes, I will do the opposite probability, because then I can just do 1 minus and give them the actual question they want, the answer they want. Okay, maybe. Now, this is all on the backs of, do you understand the formula and what it requires from us? Right, this good old formula I had up here earlier. That's the binomial probability formula. Any situation where there are exactly 2 possible outcomes, where the probabilities add to 1, and there's a set number of things or people or flips of a coin or whatever it is, you could use this formula to figure out individual probabilities of success. It's not me, Your Honor. It's the judicial system. What is in this bottle? Okay, so anything else from homework? There is a problem that if I don't get that question, I'm worried. And you're all like, I don't know what to tell you, man. There's a problem about getting a certain amount of money for a certain roll on a die, I think it was, or yeah. Which one was that? Somebody was asking me about it in my office hours.
74.
74? I like it. So let me show you a problem that's sort of related to that. But what happens when you turn 25 related to cars?
You get to rent one.
Okay, good. That's like health insurance. Your car insurance goes way down because statistically speaking, once you enter that interval of ages, you suddenly know how to drive better, right? And of course, it's based on observations made. But how do they figure out what that premium is going to be? So let's do a very small example. Let's say that we set up our own auto insurance thing. And what we determine is this. We figure out that the probability that we have to pay $100 in repair costs, are you guys with me? The probability of that equals, let's say, probably of $100 is 0.35. Pay like $1,000, probably of $1,000 is, let's say, 0.41, and then pay $10,000, probably of $10,000 is 0.24. Yeah. Okay. What I kind of left out was no, but let's just pretend like this is just for people that have accents. So, in the problem about the rolling the die, it says if you roll a 5, you'll get $10. If you roll a 4 or 6, I can't remember exactly what it is, you'll get $5. So what I put here is not 1, 2, 3, 4, 5, 6. I don't care specifically about what shows up on the die. I care how much money I freaking make. So what I should put here is 10, 5, and -6, because I make 10 sometimes, I make 5 sometimes, I lose 6 sometimes. The probabilities come from which sides of the die give me those. If 3 sides of the die give me something, that's a 1/2 chance, 3 out of 6. Maybe. So what you put here is the actual physical outcomes. Right? So rolling a die is just the middleman. The actual physical outcome is them giving me money or me giving them money. Okay, so if you've tried that problem out, you know what I'm talking about. If you haven't yet, make a little note to yourself. I basically gave away the first step of the problem just a second ago, if you're paying attention. Now here I've got what? What's going to go here? You know, 100, 1,000, 10,000. And the probabilities of each are just given to us directly. 0.35, 0.41, 0.24. Thankfully, those add up to be 1. Now, who remembers how to figure out the average? What's the average expected payout that my little insurance company is going to be expected to make? And do you understand how that's going to help me figure out how much I want to charge people so that I actually make some profit? Right? How do I figure out the average? What column do I need? X times P of X. I love it. And the mean is going to come out to be the sum of X P of X. The mean very often is called expected value, and why is that kind of nice to remember? Because what's the first 3 letters of this really? EX freaking P, expected value. Holy shit, that's nice. It's just coincidental, but it's nice. The expected value, which is another name for the average, is the sum of XP of X. EXP. All right. And we talked all about why this formula makes sense and how it relates to the way we did it before. I don't want you to just go, it's because it's EXP. No, that's not why that's the formula. It's just a nice thing that happened. So 100 times 0.35 is... Good. You move the decimal over once for each 10. So 1,000 times 0.41 would be 1, 2, 3, yeah, 410. So then 10,000 times 0.24, 2400. I moved over twice here. There's 2 zeros. I moved over 3 times here. There's 3 zeros. I mean, multiply by 10. Please, dear God, look. Our number system is based on 10 because we have 10 fingers. If we had 8 fingers, our number system was based on 8. And when I teach 120, I teach you what that would look like. I won't do that to you now. So what do I get for the average? The expected value. 2850? 28? 45? Okay. So then what do you think I'd set my premium at? Whatever kind of insurance is, I didn't even tell you what kind of insurance this is. It doesn't have to be auto insurance. What would I set my premium at? Well, I wouldn't set it at $28.45 because then I'd expect to break even on average. So I'm going to set it to however much above this I need to, depending on how many people I've got as a part of my insurance. If I've got a few people, then I might set it much higher than this. If I got like 8,000 people, I don't have to set it that much higher than this. So what do people that work for insurance companies, what are they constantly doing? They're constantly adjusting all these probabilities based on data, which changes your premium, right? And then, of course, when you transition from one group to another, like you move, and then there's a different probability for accidents in that area. You get older, there's a different probability for accidents for those kind of people. You are a good student, whatever, you get a good student discount because there's a less chance of you'll have an accident if you're a good student, which is a true thing. Do you guys get that idea? I mean, this is where this is used in real life. This is one place for setting premiums, right, based on probabilities. So there's people called financial analysts, right? Part of their job could be doing something like this, keeping on top of all the probabilities. I like it. Okay. So that 74 is going to look sort of like this. It's just going to be easier than this. It's going to be based on rolling a die. So you're probably going to all be out of 6 something. Anything else from the homework stuff? Chapter 4 stuff, anything? Okay. I'm going to assume you're doing it because you're smart people. And you know that's a good thing to do. So we're about to transition. Chapter 5 is sort of a go-between. Chapter 6 is going to be one of the most important sections in this whole book. It's going to lay the foundation for what we're going to be using almost the entire rest of the semester. So I can't put a strong enough emphasis on the fact that you desperately, when we get to chapter 6, you need to be on it, doing all the homework, making sure you understand what the hell it's talking about. Right? Just to remind you guys, there are tutors. There is me. Right? I do have office hours. I will help you if you come to those office hours. It's crazy. I'm a teacher for a reason. I want to help people understand this stuff because I love this stuff. Right? And you're all like, you would. All right. So what I want to do is I want to give you a couple examples to explain a very basic idea. Let's say I had what is mostly a circle. Looks like somebody has some slight bumps there, but it's all right. And let's say it's sort of like a game of darts. Okay, let me just make it a little bit more straightforward. It's not exactly normal darts. There's no little bullseye. There's these sectors, right? And if you get in this sector, you get 20 points or whatever. It doesn't matter. Each sector is a different amount of points. If you throw a dart and it lands in the circle, what's the probability it lands here? If you just throw it randomly at that, what's the probability it lands here? Yeah, 1 out of 4, 25%. Why? Yes, I love it. I love it. So the entire circle, if I'm talking about just darts that hit the circle. So if when I play, people step back. Because it's probably going to hit the wall. It's going to hit my little brother. Ow! What are you guys doing? It's the what of this. If the whole thing is 1, because if I'm only counting the ones that hit the circle, then what's probably hits the circle, 1 is going to hit the circle. I'm only counting those, right? I'm going to eliminate the other ones. They never happened. They're not a part of my sample. So it's probably a dart hits the circle that I will take into account, 1. So this represents a probability of 1. The area of that circle is a total of 1. So then what's the area of this part? 0.25. Right, so in a very fundamental way, the areas relate to probabilities. It sounds like when I slow down like that, it's a good note. So if I can draw a probability distribution I can answer questions about it by giving the areas associated with the question. What the hell do I mean? Yeah, are you asking me? There's a very basic probability distribution called a uniform distribution. Let's go there. This one is one we start with because it's the simplest distribution basically that exists. Uniform, that word uniform, what does it mean? The same. That's why we use the word uniform for things that, cops wear this uniform. Well, it's uniform because everybody's got basically the same outfit. Are you with me? So it's uniform. So if I were to graph it, let's say that a very common example is you're waiting for the bus, and bus wait times are uniformly distributed from 0 minutes to, let's say, 16 minutes. So what that would mean is that if I graph it, it's going to be from 0 to 16, and it's going to be all uniform. Nobody's going to be higher. It's sort of related to histograms. In fact, I'm going to relate it directly to histograms in a minute. But if all of them are the same height, does that make sense how to draw this? Now, my next question would be, what's that height going to be? So that's what the probabilities all look like. They all are uniform. They're the same probability all the way across. So how tall do I want to make this thing, considering what I just said a minute ago about the circle? I don't want to make it 1 because then the area would be 16. What do I want the area to be? 1. Why do I want the area to be 1? Because these are all the probabilities, and I want the sum of them to be 1. I know right now you're all like, what is my homework going to look like for this shit? But I'm developing right now the idea. This is not going to be something you have to do on your own. I'm not going to give you a different shape and then go, figure this one out. Right? There's uniform probability distributions. That's what we're going to look at. And then we're going to get into normal distributions. Kind of a big step. But does anybody know how tall I want to make this thing?
1/16.
Beautiful. How wide is it? 16. So how tall does it have to be so the area is 1? Well, what do you multiply by 16 to get 1? 1/16. So then if I ask, let me see if you guys see that. That's basically how all uniform probability distributions work. And just to let you know, there are triangular distributions, there are parabolic distributions, inverse parabolic distributions. There's all these kinds of distributions, but they all have the same idea. I want to make the total area of it, however far it goes over, I want to make the whole area 1. Because then when I ask a question like this, what's the probability somebody has to wait from between 2 and 7 minutes? Can you draw that on the picture? Don't change the picture, just add that little area, right? So it's probably, it takes somebody, they have to wait from 2 to 7 minutes. Good Lord, my scale is interesting. All right, just let it go down, that's fine. Shut up. It's a little better. Well, it would be what? How do I figure it out?
Subtract it from the total.
Second, yeah. What's the area of this little purple dude? Because that is this question drawn out. That's the part of the whole thing that relates to the question. Well, what's the area of that part? How wide is it? 5. And how tall is it? 1/16. So what's the area of this? 5/16. And the area of a probability distribution that's been drawn out equals the probability of that piece. So 5/16 is the probability that they wait between 2 and 7 minutes. Bam. So fundamentally, if I draw the distribution out, the answer to any question about stuff within that distribution is just the area that correlates to that. Just like this example, the dartboard example kind of thing. All right, so let me give this out. One side of this will make absolutely no sense yet, because this is for the future, right? The other side is what we're going to look at, the one with the little pyramid-looking deal in the middle. Sure. Sure. So what I want you to do, I've just now decided, I want you guys to do as much as you can of this. Do you need, what's up? Oh, sure. Which way is it going? That way. You can work together. That would be great if you work together. A little tear come to my eye. If you don't want to work with other people, that's fine. You could be like that.